This was the example of the dialog box with the tint shader and the distortion shader in the background. This is the example of the portrait pad that uses shaders for things like the drop shadow underneath the hairline here. This is the URL that goes to the Easy Painter website. I won't show that one again, but if you go there and try it out, the left side of the screen contains all the effects, and you can apply them live to a drawing. It's a lot like Photoshop allows you to do with their effects menu. And then this was the example of a colorful UI that you want to desaturate to de-emphasize part of the UI while the user is looking at another portion. So this is the full colored view, and this is the desaturated view. And then finally, this is the motion blur applied to a list box. As I said, I'd like to use the expression blend. Now, the benefit of using expression blend is that it has an asset pane that contains a number of pre-designed shaders. You can see there in this effects section of expression blend. And then if you have your own custom shaders, your own custom effects, when you compile the project, your custom effects will also show up on this assets pane. And then you can just drag and drop them over to your design surface. Now, I'm working in a small footprint window, and expression blend doesn't work that well when you have a 1280 by 1024 screen resolution, so you'll have to keep that in mind. If you run this on a larger monitor, it works a little bit better. I'm going to launch expression blend 4. And I'm going to create a brand new project. Now, this will work in either Silverlight or WPF. For today, I'm going to go ahead and create a WPF project and just accept the default names. And the thing about pixel shaders in XAML is that they apply to any element that's in the visual tree. So it'll apply to images, it'll apply to sections of your UI. Any portion of your UI can have an effect applied to it. So for today's demonstration, I'm going to use an image because it's most dramatic and it's the quickest to build for a demo, but again, it'll apply to any part of your UI. So I'm going to go ahead and add an existing asset to my application. So I'm going to click on the Projects tab, and I'm going to go right-click here and choose Add Existing Item. And I'm going to be working with this picture here called Big Eye. So I'm going to go ahead and choose this, and then see Big Eye shows up in my list. Then I'm going to go to the Assets pane, and one of the places here I can go is I can go look at Media, and my Big Eye.jpg will show up there. I can then drag that over to the artboard here and start working with it. What I'm going to do is I'm going to create a slightly smaller version of this. I'll shrink it down so it's a little bit easier to see. And then I'm going to copy it and paste in another copy of that eye, and then I'm going to reverse it. And the way you can do that in Blend is grab the side of the image and slide it over past the other side, left side over to the right side, and then I can create this kind of weird-looking alien face. Like that. Next, I'm going to apply a shader. Now, I'm going to apply one of the existing effects. They're in this Assets section. You can see there's a number of bloom effects, and there's one for applying a color tone, the standard drop shadow, and embossing type ones, one for changing it into a grayscale, and other fancy distortion effects down here. I'm going to pick this one called Magnify, and I'm going to drag it over to this picture. Now, what I want you to keep an eye on over here in the Objects and Timeline, I currently have a layout grid, and I have 2 images inside that layout grid. So when I drag the effect over, this one here called Magnify, you'll see that it distorts the eye, and it also adds a magnify effect underneath this image. Now, when I click on the image in the Object and Timeline, I'm editing the picture, and when I click on the magnify effect, I'm changing the effect itself. Now, before I continue, let me add another magnify to this other eye. starting to look like an alien. And then I'm going to click on the magnify effect here in the Objects and Timeline and go over to this section of the screen over here. And this is where I can edit the exposed properties on this effect. The author of the magnify class, they created a .NET class. In particular, they created a dependency object, and they exposed dependency properties on it. And each one of those dependency properties shows up as a property that I can edit inside Expression Blend. So now I'm going to take this center property, and I'm going to move it over a little bit and then up the screen like that. Then I'll click on this other magnify effect and do the same thing. Trying to make it look like she's looking down towards the ground. All right. Next, I'm going to tint the skin a different color, and we're trying to go for an alien look here, so I think a green would be appropriate. Now, if I were to drag this color tone effect over to the image, I would lose my current effect because you can only have one effect per element. And so I have the magnify effect currently, but if I were to drag it over, it would replace it. So what you want to do is create a wrapper around the element, in this case around this image, and that can contain multiple children. And then I'll put one effect on the wrapper and one effect on the child. Now in Blend, you can do that very easily by right-clicking on the image and choosing Group Into. And then I can pick these other containers. I'm going to pick the canvas. Now you'll see that there's a canvas wrapped around the image, and then inside the image is the magnify effect. And I'll do the same thing for this image down here. And then finally, I'm going to drag this color tone down and drop it on top of the canvas. Then once that's done, then I can choose the saturation level for this effect, the tone amount to apply, and then the two colors that are being intermixed on this image. So this one's kind of a green color. I'll make this one maybe it's kind of an orange color. So you get the idea. Right? So these effects are very effective, no pun intended, on changing the way these pictures look. Right. Now, I'd also like to do a custom effect. To do that, I'm going to add another page to my application. So I'm going to right-click here and choose Add New Item. And then I'm going to select Window. I said Page, but I changed my mind. I'm going to do a Window. Like so. Then click on OK. And then I'm going to drag the big eye over again. And now I want to add a custom pixel shader. Now we're going to dig into how you do that a little bit later in this webcast, but the main idea is you create a binary file that's going to get loaded into your GPU. And that usually has a PS extension on it, so it's a compiled binary file. And then you create a .NET wrapper class that loads that binary file, is responsible for making sure that it gets loaded into the GPU, and then it exposes properties to the .NET developer to manipulate that shader. So I already have one of these written. I'm going to right-click on my project and choose Add Existing Item. And then I'm going to go to my Assets folder and go in this Invert Color Effect folder. And here's my binary file, and here's my CSharp file. And you notice if I open this up, you'll see that it's a CSharp file that's got a class called Invert Color Effect that derives some shader effect. Okay? And again, we'll learn more about how that works in a few minutes. And here's my binary, so I'll add those two to my project. So there they are. Now I can compile my project. There's one more thing I need to do, and you can't do it from Expression Blend. I need to mark this PS file as a resource for the project. So in order to do that, I'm going to use a feature of Blend, which is to edit this application in Visual Studio. They share the same file formats and the same solution formats and the same CSproj and VBproj format. So I can just click here. It'll take this project, load it into Visual Studio. Expression Blend 4 works very closely with Visual Studio 2010. And the new version of Visual Studio 2012 has a different version of Blend that's affiliated with it. And I'm not using that version yet because it's not ready for the current version that works with desktop applications is not ready for go live, so I'm using the older version. Okay, so here's that project. I'm going to save everything, and then I'm going to go to this PS file, and I'm going to mark the build action, tell the compiler what to do with it. I'm going to tell it to mark it as a resource. All right, then I'll save everything and build the solution. And then I have to do one more thing. Inside this invert color effect, I have to load that resource. And in order to load it, I have to use a URI. And it needs to have the name of the project. So the name of my project is WP Application 3, WPF. So I'll make sure I save that and then build it. Then I can switch back to Expression Blend, and since they share the same file format, Blend says, I see you made a change. Would you like to load the changes? I'll say yes. And then I'll make sure I can build everything in here. You can do a Control-Shift-B inside Expression Blend, just like you can in Visual Studio, to compile it. And then I'm going to go to my Assets folder and look and see if I have a new effect. I do. I have this new effect, and if you see in the hover tip, it says it's part of WPF Application 3.exe. So I'm going to take that and I'm going to drag it over. This happens sometimes in the demo. Sometimes I have to compile it 2 or 3 times to get things to work. And knowing that this might happen, I have a pre-built one. Let me open that one. Here you can see it applied. So I'll drag over a new copy of the asset. Right, and then I'll go to my effects, and I'll drag over the invert color. And you see how it applies it just like any other shader. All right, so what exactly are shaders? Shaders in the desktop world are effects that are applied, usually they originally came from 3D rendering systems, and they were applied for things like texture blending and lighting model computations. And over the last 10 or 12 years or so, they've been modified in many different ways. Most modern movies that you go to have some sort of shader playing in the background if there's any sort of effect inside the movie. Now, there are 3 major categories of shaders. There are what are called vertex shaders, which manipulate a single vertex point. If you've got a 3-dimensional object and it's got a mesh that's defining the 3-dimensional model, each one of those points on the mesh can be manipulated using some code inside the GPU. So I can transform the model, I can put skin on it, I can morph it. There's also a geometry shader, which outputs extra vertexes from the input. So I already have a triangle mesh. I can add programmatically in the GPU extra points. So you can use this for things like growing fur on the outside of a model. And sometimes it's used for particle system generation. There's a lot of things you can do with that. And then the one we're going to concentrate on this week today is the pixel shader, which is responsible for morphing the color of a single pixel. Now, of course, an image has thousands of pixels, so a pixel shader is going to affect all of them, but from the perspective of the code that you're writing, it affects a single pixel. Now, these shaders are combined into the pipeline inside the GPU. So first comes the vertex shader, if there is one, and then it feeds its output into a geometry shader, if there is one, and then the output of the geometry shader gets fed into the pixel shader, if there is one. And so if you and I are going to write a custom pixel shader, we're going to be writing ours at the end of the pipeline. And in the .NET world, the input for our pixel shader is going to come from an image or part of the visual tree. So in essence, WPF or Silverlight, what they will do is they'll turn the output of the visual tree into a texture They're going to load it into one of the registers inside the GPU, and then our pixel shader can pick it up out of the register and start manipulating it and changing the pixels on it before outputting it to the monitor. And so basically your Vertex goes through a rasterization process, and then that image can be manipulated by the pixel shader. So all of this is transparent to us. I explain a lot of this in the beginning of my book, how this works. Okay, I have a question. So does WP8, is that Windows 8 or Windows Phone 8 support GL shaders? Is the question I'm seeing here from Oswald. And as far as I know, there is no support for, you're talking about OpenGL shaders? As far as I know, there's no support for that. In fact, the phone itself has had no support for shaders at all. So this image here represents a mesh, a three-dimensional object, and those little purple and yellow points on there represent the mesh points. And so you can imagine if I was creating a vertex shader, I could move this yellow point here. I could take that yellow point right there, and I can move it to no location. Let's say I moved it over here, this area. Well, what that would do is it would appear to distort the shape of this object. Right? If I were to start adding extra points on here and then moving those, then I'd be programmatically enhancing the shape of this. That would be the geometry shader. And if I were to change this one pixel from purple to blue, then that would be a pixel shader. Now, pixel shaders can also make things look like they're moving to new locations, because what I could do is I could make some copies of the pixels that are over here, and I could move them over to another location in the pixel shader. So what that would do is it would appear to distort the shape. Now, I'm really not changing the 3D model. At this point, it's already been rasterized, and I'm just working with the pixels themselves, but it will still look to the end user like it's being distorted because we're moving and shifting the pixels around. So if I were to use something like a sine function to take all these items along this edge here and move them, we can make it look like a wavy line as it moved down there, because some of the pixels would be moved to the left and some of them would be moved to the right, and we do it in a fluid fashion. So that's how you get effects like ripples. You're moving items from their original position to new items in the pixel shader, and you're doing it with an algorithm that makes it look like it's a wave on the water. Let me show you one demo. From DirectX. Now this is a live DirectX. Now DirectX is the 3D engine and a lot of other things for Windows. And this is a model here. And I'm going to zoom in so you can see the model. And this has it's distorting the model shape. So it starts out thin and then gets fatter. I don't know how well this plays out on the virtualized desktop, but you see it's getting fatter by we're stretching those vertex points out, and then we're shrinking them down using an algorithm to make it look like she's a balloon that's being inflated and deflated. Here's an example. Now this could be done using a vertex shader. We could be changing the shape of this flat what looks like a rectangle, or it's possible we could change this with using a pixel shader by adding ripples and recolorizing some of the pixels. So it's taking some of the pixels and making them white, that's the original color, and making some of them grayscale and some of them black. Okay. So DirectX, as I just mentioned, is Microsoft's 3D graphics framework. It supports all shader types. In WPF, it directly works on top of Direct3D, so that means that we can leverage pixel shaders in our application. Microsoft also has other frameworks that work with shaders. There's a really excellent one called XNA, which has support not only for pixel shaders but for vertex shaders. However, and since this is a XAML talk, there's not a XAML solution for XNA. It's still used for game development, though. Then there's the upcoming Metro XAML, which runs on WinRT. There's no native support for shaders, although there are ways around that. And then the Silverlight XAML engine, the thing about Silverlight is it runs on a virtualized GPU. And so it can also use pixel shaders, but it's not actually running on DirectX because Silverlight runs across platforms. So it can run on a Mac and it can run on a PC. So since the Mac doesn't have DirectX, the Silverlight team had to create this virtualized system that would mimic what DirectX is doing. And so it's running in software. It's not running in your GPU, so it's never going to be as fast. However, it is multi-core, so it'll use multiple cores if they're available on the end user's computer, and it's still faster than other solutions that you can do in Silverlight, like writable bitmap. So here's an example of a writable bitmap in Silverlight 3 that did 19.45 frames per second to run a demonstration, and that same demonstration done with a pixel shader was 139 frames per second. So it kills the speed of all the other mechanisms for manipulating the pixels on the screen. It's not as fast as the WPF version, but still faster than all the other solutions. And of course, that's one of the reasons why we love shaders is not only they do cool effects, but they're also extremely fast. And the reason they're fast is because they run on the GPU. I thought I would go over a few of the categories of what you can do with effects. Right, so obviously one of them is a color modification. If you're manipulating pixels, you can take the original pixel and turn it into another color. And if you don't move it to any new location, it's just a color modification algorithm. So one common one is grayscale. Here's one that's turning it into black and white. So the original picture's on the right side of the screen, and the one with the shader applied is on the left side of the screen. Here on the bottom right is one that has a tint shader where it's been turned into a grayscale. All the pixels have been turned into gray colors, and then we've applied a overall color to that. This is what's called color mapping over here. What we've done is we've taken two images. Shaders support up to 4 inputs. And so I can take 2 inputs. One of them is the picture of the woman, and another one is a picture that contains just a set of colors. And then what I can do is I can take the grayscale value, and if for every value in the 256 range of grayscales, I can take 1 pixel out of the color map and apply that. So the color map that I applied had yellow, green, and black in it. And as it's moving through the lightness and darkness of this picture over here, it's using the colors out of the color map to redraw. This is an excellent animation system. If you run this animated on your application, you can get some really cool effects using this. Here's some what I call distinctive effects that don't fit in any one category. There's pixelate, making it blocky, old movie effects, parametric edge distortion, and sketch effects. We've got distortion and displacement. Here we're moving items around on the screen. So here you can see the classic ripple effect. So what we do is take these pixels and move some of the pixels a little further up the page, and give them up further down the page, and it makes them look like they're bunching together in areas and stretching apart in other areas, and so we end up with these ripple effects. Another distortion effect, a mirror effect. And then, of course, the blur, when you use a tool like Photoshop, it uses a blurring algorithm. These are typically implemented using something called a convolution filter. And I have a section in my book that talks about convolution filters and how you apply them in a pixel shader. You can also, since you have more than one input, you could supply 2 inputs to a shader, picture A at the top, picture B at the bottom, and then as you go from one picture to the other, you can apply a distortion effect that morphs the pixels of one picture more than the other. So you can get this transition when you move the users from one area of your application to another. You can do it through a transitional effect. And again, this will be much faster than if you're to do it using other techniques. All right, let's talk about writing some XAML shaders. There are two parts to a successful shader. You have to write an unmanaged GPU-specific code, and that's written in a language that was developed by the DirectX team called HLSL, high-level shader language. And this is a step up from the old way that we used to write shaders, which is using assembly language. And the point is that this unmanaged GPU has to get compiled into a binary that the GPU understands. And just like for applications you run on your own local computer, we don't want to code in assembly anymore. We want to code in a higher level language. Now, HLSL looks a lot like C. It has curly braces and has a lot of the same keywords. I have an entire chapter in my book dedicated to the syntax of HLSL. Right? And then you have to also write a managed .NET wrapper class that's written in any .NET language, but the two common ones are C# and VB. And this will be a dependency object that derives from the dependency object-based class, and then you expose dependency properties. So each item that can be manipulated programmatically in the unmanaged shader usually also has a managed property inside your shader effect class that is used to bind to and run animations on and those other things that you would do in a WPF or Silverlight application. GPUs are parallel in nature and designed to run concurrent operations. Essentially, they are packed with hundreds of data parallel floating point processors. To take advantage of data parallelism, you create code that works with a small, isolated portion of a data structure. If done right, the data modification algorithm can solve the problem while running simultaneously on many processors. The data structure for a pixel shader is the image data, and the data modification algorithm is the custom shader code. So your pixel shader function is run once for each pixel location, with many instances of your code running simultaneously on the GPU. So your HLSL code is responsible for outputting the color for one pixel. Right? So that's one of the things that's different about developing HLSL applications is you think of your algorithm you're writing from the perspective of a single inbound pixel. And in order to process all the pixels on a 1920 by 1080 monitor, the GPU runs the shader algorithm more than 2 million times once for each pixel. But currently, there's no consumer-level GPUs that can handle 2 million transactions in one pass, so the job is typically divided into sub-batches. The more powerful the GPU, the fewer batches that are needed to run the shader to completion. Now, parallel processing requires a different mindset from traditional single-path development. Thinking in terms of columns and rows, dividing an image into a checkerboard of tiny squares is wrong-headed. You need to modernize your brain and embrace the notion of the single pixel algorithm. Shaders can read from multiple inputs, as I mentioned. These are called textures. They're stored in the GPU registers. And then shaders can also take numerical inputs. These are known as shader constants. So these can be floats, or they can be combinations of floats. So this is one of the quirks of HLSL is that I can have a float value of a variable, but I can also use something called a float 2 or a float 3 or a float 4, and I can have matrices of floats. And then when I declare a float 2 variable, what I'm basically saying is I want to have one single variable that contains 2 float values. So that would be like the implementation of a point. And if I have a float 4, that contains 4 float values, and that you can think of that as a representation of a color. The alpha channel could go in one float, and the red and the green and the blue channels could go in the other 3 portions of the float. And so when a shader returns a piece of data from the main function, it's actually going to return it as a float 4 because that represents the outbound color of the algorithm, the final value of the pixel that you're changing. Right? Now these are passed into shaders via shader constant registers, and these registers are indexed. C1, C2, C3, and S1 for the texture source images are S1 through S0 through S3, I should say. Okay. I'm almost ready to write some HLSL code, but let's talk about the steps you have to go. Just to review what we've talked about. To create a managed effect class, you need to write some HLSL code, and you typically store that in a file with an FX extension. Then, since you're targeting a DirectX application, you're going to run the DirectX compiler called FXC. And in order to run this, you have to install the DirectX SDK. Now, the DirectX SDK is over a gigabyte in size, and you need to install that entire thing to get one executable. Right? Now, when you compile that, you turn that into a PS file. Then you're going to create that .NET class that's going to derive from shader effect. So there's this effect class, and then there's a shader effect base class, which is marked as abstract. So if you're creating your own class, you're going to drive off this one as your base class. And then the next steps is you have to write some code that loads the shader binary. I showed you that a few minutes ago in when I did that custom shader. I had to change the URI that tells it where to find the embedded resource file. Right? Then I need to register my code with the registers on the GPU. I need to create some dependency properties. I need to optionally create some .NET property wrappers. I need to compile my WPF and Silverlight class. I need to use my shader class in my XAML code. And if I want to see what it looks like, I have to run the application and actually demonstrate it and wire up animators and things like that. And there's a lot of steps involved in that. So that's why I created a utility called the Shazam Shader Editor. Now, the Shazam Shader Editor is available for free. It's at shazam-tool.com. Our website just went live late last night. So you can download the latest copy. It just debuted, version 1.4. It's free, and you can get your copy of this from there. And it's basically designed to help you streamline the writing and testing of shaders. So let's run Shazam. I'm going to go to my Start menu and open all programs. I know you probably can't see that on my virtual desktop, so I'll scroll it up so it's a little bit easier to see. And I've just installed it this morning. Here's the latest version, Shazam Shader Editor. One of the features I added in this is I added IntelliSense to the code editor. So we'll give you a 10-minute tour of this application. The way this works is you have an editor window here that's color-coded, and it has IntelliSense now, so that as you're typing in here, you get a drop-down list to choose from of the registers I'm going to plug this value into. And then I get a tooltip that pops up over here that specifies help of what that does. Most of the other editors are just text editors, and they have no IntelliSense like this. Okay. It also supports undo. And what you're going to do is you're going to write your HLSL. Now up here you can see that I have an input sampler, sampler 2D, which is my texture, and it's loaded in one of the sampler registers. And then I have some parameters here, angle and blur amount. These are stored in those constant shader registers. And then down here is the main body of the HLSL. You always have to have at least one function in an HLS shader, and it has to be, when you compile it, you have to tell the compiler what the name of the function is. Shazam assumes that the name of the function is main. And you see that it takes a float2 in, which represents a coordinate inside the source image, and then it outputs a float4, which represents the new color for that pixel. Okay. So you write your shader here, and I'll show you a brand new shader. I'll create a brand new shader file. It's going to create an FX file. Okay. And then it stubs in some boilerplate HLSL. And then when you create your shader, you can compile it without having to install the DirectX SDK. And then you can apply that shader to your picture up here. Now, while I'm compiling it, it's also generating the C# file automatically for you. So the C# class was created over here called live demo effect, and it derives off shader effect, and it also creates your own dependency properties. So there's one dependency property that registers the input the pixel picture that's being loaded in. And then I have a single constant register here called sample input param. I'm going to change that and say this is going to be the blur amount. And I'll save this, and then I'm going to recompile. And if you go look at the generated shader, you'll see that how come I didn't not seeing the there it is. So it renamed that dependency property to blur amount. And so then what you do is when you're ready to use this in your application, you go to Tools, Explore Compiled Shaders, and for every effect that you've compiled with Shazam, it creates a folder for you. Here's the one we just created, and it's got a copy of the CSharp file and the PS file and the VB file. So like I did earlier today, you would copy these two files into your project, go and mark this PS file as a resource, change the value here, the name of your project. Now, Shazam can handle this for you. If you go to Settings and you type in your namespace here, when it generates the output, it'll automatically change that, so you don't have to, when you copy it into your project, you don't have to change it. Okay? And then you get a set of sample images here to choose from. So there's one image that you can customize. You get a number of samples. You get a color wheel for trying it out on all the 16 million colors. And then you get one for testing distortion shaders, one for testing a shader on a UI, one for testing a shader on a video, and then one that lets you compare the original image and the effect applied to the image. I'll choose this picture of the fire and the road, and I'll go in and look at the next part of Shazam, which is you can go to this thing called Shader Loader, and Shazam ships with some sample shaders, and it also ships with a tutorial. So there's a self-study tutorial, and then all the examples that are in my book are in this folder. So every code example that's in my O'Reilly book will be listed in here. So you can click on this and load. I have to go back to here. This is one of the examples from Chapter 6. Okay. And then it also comes with sample shaders, and there's about 100 sample shaders that are included. So you saw the blur one. There's also color mods. There's the bloom color mod, and there's one called the bright extract. There's the invert color we saw earlier today, so on. And of course, the fun ones are all the distortion ones. These are the ones like the banded swirl. Now, you can also go up here and choose full screen image to see what it looks like for a large image. You can also do a full screen code if you want to have more room for writing your code. Press escape to go back out. And then another feature that I created was the ability to test this out. So you can click here and go to the tryout. And if you'll notice that this shader has these constant registers. So it has one called center, and one called bands, and one called strength, and one called aspect ratios. And those are dependency properties on the type. And when you click on the tryout tab, each one of those properties is turned into a testing harness. And Shazam's smart enough to know that the center point was it was implemented as a float 2, so it has 2 parts. So it creates an item with 2 sliders to manipulate the value. Right? And since I don't know what your minimum and maximum values are for your shaders, I put text boxes in here so you can type in the value that you want. Like down here, I can go from band 0 to bands 20, right? And if I think that it should have gone to bands 40, I can just type a new value in here, and Shazam automatically updates and lets you now go to 40. And another thing that I did is I got tired of hand manipulating all of these, So I wrote an animation tool, so you can click here to animate that. Let's slow that down, we'll do 9.5 seconds. So it'll animate this from 9.5 seconds from moving the center point. And if I want to move it around the circular, the outside edges, I can click on this one. And then I can also start animating the bands and animating the strength and get some really wacky looking effects. So we've got about 5 minutes left. So we'll spend the last 5 minutes or so looking at the HLSL that we write. All right, here's about the simplest possible shader that you can write. It has an inbound sampler. I didn't even specify what shader register for it to go in. Don't want to see that during a demo. But when you download your free copy, if you have any bugs, you can go to Help and report a bug. Also, if you forget, you haven't bought your copy of the book today, you can go here and it tells you where you can get a copy of that. So let's try this again. We're going to go to Book Examples, this one right here. That's about the simplest one you can create. And it's a float main that returns a float 4, takes a float 2 as an inbound, calling that the location and source. And then what I'm using is one of the built-in functions that's part of HLSL, which is called Texture 2D. That's used for sampling one of the pixels. So remember that your algorithm has to assume that it's taking a single pixel and it's going to do some work on it. It's going to output a color from that pixel. So this is how you select it. You get the location in source, and you can go to this XY property here. This is called swizzling, how you can combine more than one parameter in a single dot operator. So what this is saying is get the X and Y coordinate and go into the picture and sample out that pixel and then return it. So since I didn't apply any manipulation to it, I get the picture looking exactly the same as it always has. But if I write a little bit of code in there, so now I'm sampling the inbound parameter, right, one of the pixels, and then I'm going to do a brand new color. I'm going to say create a new float 4. This is a function, and I'm saying take the alpha color, the alpha channel, and subtract the RGB. Again, this is using all 3 channels. Now I can also subtract just the red channel like this. And when I compile it, I have to change this first item too. So I could say something like, say, color R or color B minus color R, and then I have to do 2 more parameters, comma, color G minus color B, comma, color red minus color green, and now see that will compile. Oh, it's got an error, unexpected token color. Oh, I'm missing a comma right there. So now you see what I did is I swapped colors. I took the original channel, the red channel, and I said, look at the green values and subtract whatever the current red values is. And maybe I'll add one of these so it's not so dark. So I'm going to add 2 colors together. Now they'll get clamped. If they don't fit into the size of the color, they'll get clamped to the boundary, so you don't have to worry about overflow. I'm going to press F5 to recompile. Now you see I got a really bright green effect happening there. And then I have this float 4, and then I return that from my function call, and then that gets passed in. It's run against each pixel, and then outputs these new colors. Okay. The distortion shaders work by taking the pixels and moving them around on the screen. So you see what we're doing here is we're taking this again. We're doing a sample at some point in here. At some point there should be a sample. And then we're using some of the built-in functions like the sine cosine function or the remainder, the fract function, then the arctangent function and the length function. And we're reading some of these values. We're doing some mathematical calculations on them, and then we're taking this pixel that was in this location here, and we're moving some of the pixels a little bit further to the left and some of them a little bit further to the right. And it makes them look squished together, which to the human eye makes them look like ripples on a piece of metal or a water surface. Here we're using the tangent function, and we're taking this tiles property up here, which is right in this register, and we're using that to calculate tiles times 2.5 times the UV. Now UV in this case is the inbound parameter to my function right here. So I'm doing some multiplication there, then I'm using the offset value, which is another code. And Shazam does a clever thing. I had some help on getting this implemented in Shazam. We use XML comments in here. And these XML comments, when you compile your Shazam shader or the HLSL shader into the CSharp effect, it takes these comments and uses them to define the start value and the ending value, the default value, not only for the produced code, but also for the tryout tab. So you see how this is 10 right there? And if I go in and I set the maximum value of this to 20 and the current value to 3 down here, and then recompile everything. Save it. It's got a read-only problem. That's going to be interesting. I have to figure that out. So when I recompile this, I see it's not supposed to be saving it there. I have a bug. All right, anyway, when you recompile it, it would readjust this to the, I think I know why, because when I started this, I didn't start it from the correct location. Anyway, Yasmina, I think we are close to the end of the session, aren't we?
We are, Walt, and we do have a few questions that have come in.
I'm not seeing them. Do I have to click refresh?
Well, I'll just read them to you real quick. We have a question from Ben. Ben would like to know, he joined a little bit late and wanted to know if any of your presentations today will apply to Fusion, APUs like AMD's, A6 350, Llano, CPU, GPU, they tag it?
So that was from Ben? Ben, I'm not sure. I don't know if any of that will apply. I know that he came in late, so we're working with the XAML technology, and it works directly with DirectX. So I don't know.
Okay, and then we have a question from Oswald. Main differences between HLSL and GLSL for WebGL, if you could talk about that.
So the main difference is I'm not a GLSL expert. I spent, it was hard enough learning all the things to know about HLSL, but they have different syntax. They're similar in a lot of fashion, but they're also different, and there are a number of pages on the internet that talk about the differences. And then I believe WebGL, right? That's you're supposed to use the you're supposed to use the open GLSL markup language, programming language, pardon me, to work with WebGL. Is that correct? So I think what you're asking is, how much learning curve you have to go through. And the short answer is a lot of the functionality looks very similar. I have similar named functions like frac, and they have slightly different ways of dealing with things like the way variables are declared, the way float 2s and float 4s and some of the things are slightly different. And again, I don't know all the details myself.
We are going to say a big thank you to you all for presenting an outstanding webcast for us all, for sharing your knowledge and expertise with us. Is there anything additional you'd like to leave the audience with today?
I'd like to say thank you for bearing with me at the beginning as things were not working. I was getting a little anxious there, but I managed to get it done. And yes, go to the Shazam-tool website. I don't know if I pushed that link out yet. Let me push that out.
Yeah, let's push that. And I'm also putting it in the group chat for folks. I'll push it out for you. Here we go.
Okay, thank you. And so you go there and get a copy, and let me know if you're having that permission issues. Shazam is supposed to save your shaders outside of the program files folder so that it can compile them without having permission issues on your operating system. And that's why I was seeing that dialog pop up as saying that was an issue. So if you see that on your own computer, you can email directly at shazam@outlook.com. That's the new email address we just went with, and I'll get it fixed. Thank you very much for attending the virtual session.